Hi, my name is Manish Gupta, and in this video, I'm going to talk about YOCO, which are decoder-decoder architectures for large language models. YOCO stands for You Only Cache Once, and let's see what is YOCO's architecture and try to understand how it works. Okay, so it's a decoder-decoder architecture, right? So it basically looks something like this. But even before we get into this architecture, let's try to understand why people proposed YOCO. Okay. So the transformer-based decoder models actually have these key value caches, right? So key value caches are basically used so that at least the prompt part for that particular part, which those tokens which comprise of the input or the prompt, you can actually generate key values, those key value embeddings or key value caches, and store them, right? So that when you're trying to generate the next token, it basically just makes use of the keys and values at those positions, at the previous positions, and then makes use of those as to compute the next token and generate the next token and so on, right? One by one. Okay. However, these key value caches can be very large. For example, for a 65 billion parameter large language model, even with grouped query attention and 8-bit quantization, and with let's say like a little longer sequence length, 512 thousand tokens, you can easily take like 86 GB GPU memory. Now, even H100s don't have that kind of memory, right? The other problem is the prefilling latency. So remember, when you go to Bing Copilot, or for that matter, any other LLM, if you give a very long prompt, it takes quite a while for it to come up with an answer, with a response. It takes that quite a lot of time because in this time, it is trying to prefill, the key value caches. It's trying to sort of generate those key value embeddings and then store them, right? Now, the prefilling latency, if you look at it, if you're using, let's say, 4 H100 GPUs for a 7 billion parameter model with optimizations like flash decoding and kernel fusion, it still takes 110 seconds for 450K tokens and 380 seconds for a million tokens. Now, typically our prompts are not that large, right? But there could be some tasks where you may want to basically provide like a very large document or multiple documents as part of input, in which case it can actually take quite a while to do this prefilling of the KV caches, right? So that is why, I mean, to basically reduce this prefilling latency and also to reduce the GPU memory usage for the key value caches, those are the reasons why they actually proposed the YOCO architecture. Okay. So how does the YOCO architecture look like? Well, it is a decoder-decoder LLM. So it's more like the encoder-decoder LLM, where the encoder is also a decoder in that sense. Okay, so that's that. Okay. So of course you pass the input, the shifted outputs here, and essentially you generate the final outputs at the top layer. Okay. So you have a cross decoder here. Very much this cross decoder is exactly, in fact, similar to the decoder in an encoder decoder network. Okay. But then rather than the encoder, what you have is something called the self decoder. Okay. Now, this self-decoder basically generates the keys and values at every position. And these same keys and values, the keys and values, in fact, the ones that are generated for the last layer are actually used by this cross decoder. Okay. Now, how does this work out is basically explained in much more detail on this picture on the right side. Okay. So what do you observe here? So you observe that at the input, you are actually providing this input, you only cache, right? So that's the input. And then, of course, you have the embedding layer, which basically, embeds this input. And then you have, let's say, if you are trying to come up with the number of layers is L in your overall network, then the first L by 2 layers are essentially, your self-decoder. And the next L by 2 layers are basically your cross decoder, right? So the first L by 2 layers are self decoder, the next L by 2 layers are cross decoder. Okay. And as you notice, it's basically written out there as well. So L by 2 layers of self decoder, L by 2 layers of cross decoder. Okay. So now, if you notice, the self decoder essentially has, of course, it computes the QKVs, so QKVs, and then it uses the typical self-attention, so multi-head self-attention, but actually uses this efficient self-attention. Now, there are different forms of efficient self-attention. So, for example, there is the sliding window attention based on, so which helps reduce the quadratic complexity of this multi-head self-attention to make it linear, right? So it basically tries to pay attention. Every head pays attention only to a previous few positions only. Okay. So there are different ways of doing self-attention, efficient self-attention. A sliding window is one of them. The other way of doing it is called gated retention. Now, I'll not go into the details about how these things are done, but that's that, right? So essentially, so QKVs are computed using this efficient self-attention, and then you have a standard feed-forward network. Of course, there is pre-normalization. There is residual connections and so on. Okay. Now, what happens in this upper part, right, which is basically called as the cross-decoder part, is that you take these key value pairs, the keys and values, which are basically being computed by the last layer here, and those are the ones that are cached and used as part of cross-attention. Okay, so as you see, the keys and values are actually coming from the KV cache, which is basically populated here. This KV cache is actually populated by the last layer from the self-decoder, right? And then the cross attention essentially takes the output from the last layer of the self decoder and uses it to compute queries, but the keys and the values are not recomputed. They're basically just used from the cache. Okay. So that's the interesting part. Now, this architecture actually makes the processing super efficient. Okay. So let us talk about how efficient it becomes. So, or rather, again, broadly, just to summarize, the YOCO architecture actually consists of a cross decoder stacked upon a self decoder, as you saw, right? And then self decoder sort of encodes the global KV caches that are reused by the cross decoder via cross attention, right? So essentially, the self decoder is basically at the last layer encoding the global KV caches, global meaning the entire sequence, right? And that are reused by the cross decoder. Okay. Now, this is very, very efficient. Why it is efficient? Well, you can actually see it here. So if you look at the KV cache memory, a typical transformer basically requires of the order of L and D cache memory, right? So where L is essentially the number of layers in the network, N is the size of the input, so the sequence length, and D is the dimension size. Okay. So essentially, the KV caches, of course, for every position, for every layer, you have to basically store keys and value embeddings, right? So therefore, L into N, and then the embedding size being D, so therefore OL and D. Okay. Now, in YOCO, what happens is that the self-decoder is effectively an efficient attention mechanism, efficient self-attention mechanism. Okay, so it basically means that rather than using quadratic attention computations, it basically just uses your typical linear kind of computations. Okay, that's one. The other part is that which basically means that rather than keeping all the key value key values in the cache for all the L position for all the N positions, right? What you would do is to rather keep the key value caches for each of those layers L, right? Only for a few positions, let's say past 4 positions or 3 positions and so on. So what this typically means is that you end up with the O of L into D as your overall KV cache memory size. However, there is an interesting part here. Now, since you have to basically also maintain this global KV cache, what you need to do is to essentially compute the key values for all the N positions at the last layer, right? So therefore, this N into D term comes here. Basically for the last layer, you still need to store the keys and values, those embeddings for all of the positions together. Okay. So, but all in all, as you see, right, rather than O, L, and D, you are basically using O, N plus L into D, which is much smaller. Okay. Now, how about the prefilling time, right? So for the prefilling time in a standard transformer, you would require order of L N square D. Why? Because, well, when you're prefilling, it's quadratic. I mean, of course, you have to prefill for all the layers, and dimension D is the dimension size, so that's obvious. But N squared, because for every position, you have to actually compute the attention with respect to or rather the keys and the values. For in a quadratic manner, right, with respect to each of those other representations, right? However, in YOCO, that thing becomes LND. So that thing becomes LND because of 2 main reasons. I mean, the prefilling time reduces for 2 main reasons. One, rather than actually doing prefilling for all the L layers, you actually need to do just for L by 2 layers, right? Because for the upper part of this network, you basically are not doing any prefilling. You're just reusing the KV cache from the lower part anyway. Okay. So it becomes half, but that doesn't really matter for the order, right? But what matters for the order is that prefilling is also being done using efficient self-attention, which basically means that rather than actually taking quadratic time to do prefilling, you're actually going to take linear time for prefilling as well. Okay. So that's that. So that's the YOCO architecture. Now, how does YOCO model perform, right? So of course, the first thing to evaluate is that, hey, is it accurate enough or not, right? So what these guys did was to evaluate it on a large number of NLP tasks. So of course, I've not shown all of those NLP tasks here, but they compared it with other popular transform-based models like OpenLlama, StableLM, and then they observe that on average across these tasks, YOCO does reasonably well. Right, so essentially, 6.634 is really reasonable in comparison with the other two models, OpenLlama and StableLM. Now they try to increase the size of the model and also try to increase the compute power that is given to pre-train. So rather than 1 trillion tokens, they tried with 1.6 trillion tokens. And they did observe that the overall accuracy of the YOCO models which are trained increases, which basically means that, hey, this just does not hold for smaller model sizes and for lesser pre-compute. Lesser compute for pre-training, but it actually works for larger model size as well as for larger compute powers, larger compute power for pre-training as well. Okay. Lastly, they also tried to sort of experiment with longer context lengths, like 1 million tokens. And they observed that when you increase the context length, actually the accuracy does improve. So which basically means that yes, it is able to take care of longer context lengths nicely as well. Okay. In fact, in the paper, you have other kinds of results as well. Like they basically show that perplexity over longer sequence lengths continues to decrease, meaning the model can actually make use of longer context lengths very nicely. Right. They also try to work with the popular needle in the haystack retrieval kind of a problem, where you basically provide very large input to the model, and then you have basically have a needle, a specific sequence that you want to discover back again as output by the model. So they compared with several baselines on this particular long sequence kind of a task. And they compared with models of different sizes. YOCO is 3 billion parameter model, and they trained a 3 billion parameter model, right? And they experimented with a different number of needles. So basically n equal to 1, 2, 4, and 8, right? And as you observe, for n equal to 1, YOCO sort of provides almost 0.98, so almost perfect accuracy. Even with n equal to 8, YOCO actually gives 0.56 accuracy, 0.56 as the accuracy, which is not too bad. So it is sort of comparable in performance with respect to other popular transformer-based decoder models. Okay, so that's that. So YOCO basically is equivalent in terms of performance with previous well-tuned transformer-based models. Now let's talk about efficiency, right? So this chart basically shows you GPU memory usage, right? And on the x-axis, what you see is essentially the length of the input sequence, right? So essentially 32K, 256K, 512K, 1 million, and so on. Okay. So what do you observe here? You basically observe that even for 32K, even for this 32K sort of sizes, you observe that YOCO gives you about 2x improvements compared to a typical transformer in terms of GPU memory usage. So it takes 2x less memory, right? But if you go to larger sequence lengths, like a million, you basically end up getting like about 9.38x reduction in the usage of memory. Okay. So as you see, as the input sequence length increases, the GPU memory usage sort of increases crazily for a transformer, right? But for YOCO, well, it increases in a very minor way, right? So basically, the increase is not much. And this basically happens because, as you see on the right side basically shows you a breakdown of the memory consumption. It's basically like memory profiling, right? In terms of, so the memory weights basically consist of three kinds of things. They could be key value caches, they could be intermediate activations, or they could be other model weights, right? So the key value caches, so others is basically model activations, and these weights are like the other model weights, right? So what you observe is that in a typical transformer, a whole bunch of the GPU memory is basically consumed by the key value caches, right? Especially with 1 million sequence lengths. However, for YOCO model, as you can observe that the key value cache size reduces to just that much, right? So, and which is basically what gives you this 9.38x reduction in the overall, memory usage. Okay. Now that's about GPU memory usage. But if you think about the prefilling time, if you look at the prefilling time, Now, again, on the x-axis, you basically see the length of the sequence length, right? And on the y-axis is prefilling time. And as you can observe, even for million-sized sequences, of course, the prefilling time reduces by 72x. Now, that's huge, right? So, and lastly, let me talk about this throughput. So how many tokens it can generate per second, right? So x-axis is context length and y-axis is throughput. So as you can observe, even if with the 512K kind of sequence lengths, you basically observe up to almost like 10x throughput increase. Even with 32K sequence lengths, you observe about 2.72 throughput increase. Now, sure, I mean, if you're not doing very long a long sequence task, then you may not observe really very high throughput increases. But if you're really doing long sequence tasks, then YOCO is the way to go. Now, I mean, there are, of course, many open questions. Like, for example, why do half and half, right? In this architecture, they could have probably done L by 3 here and 2 L by 3 there. What would happen there? I don't know, right? Can you combine this kind of thinking with other kinds of optimizations? Sure, you can, but it needs to be seen if YOCO kind of architectures become more commonplace, right? Uh, Yet another interesting thing is that the current pre-trained models follow the standard transformer architecture. Now, of course, if you don't have pre-trained models, would you still use YOCO? So now all of those are open questions. And of course, time will tell whether YOCO becomes mainstream or not. Okay. So in summary, YOCO models are basically transformer-based decoder models, but they are decoder-decoder models. So there is a self-decoder and then there is a cross-decoder in that sense. They provide favorable performance compared to transformer in various settings of scaling up model size and also training tokens, right? On a 1 million context length, they basically gave near perfect needle retrieval accuracy, especially when there was just one needle in the haystack, right? And then lastly, and most importantly, YOCO basically improves the inference memory, prefill latency, sort of reduces the inference memory required, reduces the prefilling latency, and increases the throughput by orders of magnitude across context lengths and various model sizes. Okay, that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn and look at my search on my homepage.